So the first of the two first-order differential equations that we're asked to solve in this question is, let's write it out as we go along, dy by dx is equal to xy plus y minus 3x minus 3. Now, it looks very awkward, but as I said to you, that definitely the easiest way of solving first-order differential equations is to solve it by the separation of variables, if that's possible. So the first thing to do is to check whether it's possible to do it in that way. And if we start to manipulate the right-hand side of this equation, grouping together the first two terms as y into x plus 1, that's obviously xy plus y, and then we group the second two terms as minus 3 into x plus 1, that's obviously 3x minus 3, we can then see, well, let's take out the common factor now of x plus 1 on the right hand side into y minus 3. So although superficially it looked a bit awkward, this is indeed separable, because now we can write the same equation as dy over y minus 3 is equal to x plus 1 dx. So, of course, now the left-hand side is just a function of y and the right-hand side is just a function of x. We can indeed simply integrate both sides, and the integrations themselves are trivially easy. We have natural log of y minus 3 as the integral of the left-hand side, and integrating term by term on the right hand side, integral of x is a half x squared, and integral of 1 is x, not forgetting of course that there's a constant of integration. It's first order differential equation, so there's going to be one unknown constant, and again, usually, although that's sort of the solution, one strictly speaking should write y as a function of x as the solution. So let's manipulate it slightly and say, take the exponential of both sides and say, well, y is equal to the exponential of x squared over 2 plus x plus c, and this is a trick we've used before. This is e to the x squared over 2 plus x times e to the c, and so this is some constant. We could, for example, call it d, e to the x squared over 2 plus x. So that will be the neater way of writing the solution to that equation. Now the second first order differential equation that we're asked to solve, part B of this question, is dy by dx plus 2y over x equals the square root of 1 plus x over x squared. Now, try as we might, any kind of tricky algebraic manipulation we try, we're not going to separate this one. But I hope that you do recognise this is one of the forms, again, that we studied in the lectures. This is of the form dy by dx plus some function which can be a constant, it isn't here, can be a constant, p of x times y, is equal to some other function, q of x. Principle again could be a constant but isn't here, and we can immediately identify here that p of x is equal to 2 over x and q of x is equal to the square root of 1 plus x over x squared. And such equations can be solved by multiplying through by an integrating factor. Now I'm going to call the integrating factor if, so keep writing out this long expression, and the integrating factor itself is e to the integral of p dx. Again, we went through the theory of why this worked in the lecture, and so this is e to the, again substituting for p is just 2 over x dx, and integrated, and that is equal to e to the 2 log x, and this is likewise equal to e to, this is again simply algebraic manipulation, e to the log x squared. And so if you exponentiate the logarithm of something, well, you just get that function itself, so the integrating factor is x squared. Now the general solution, once you've got the integrating factor, the general solution is y times the integrating factor is equal to the integral of q times the integrating factor. Of course, q is being integrated over the variable x. So we've got now that the integrating factor is x squared, so we've got x squared y on the left hand side, and then very nicely the x squared, the integrating factor cancels the x squared in the denominator of q and just leaves us with the integral of 1 plus x dx on the right hand side. Quite a tricky problem, this one, because we're not finished yet. We've still got to actually perform the integration on the right hand side. I think a nice way of doing this is just by the little linear substitution. U is 1 plus x, and then trivially du by dx is 1, or du is equal to dx, and then we can write the integral as the integral of u to the half du, which is equal to 2/3 u to the 3 halves, plus a constant, of course, because again a first order differential equation is going to produce one unknown constant, and this is equal to 2/3 x plus 1 to the 3 halves plus the constant. So finally we now know that that's equal to x squared y, so our solution to the differential equation, the general solution that we're asked for, is that y is equal to 2 over 3 x squared. I'm going to divide through now by the x squared plus this unknown constant c over x squared. But now we're given that y at x equals 1 is equal to 1, so that boundary condition enables us to eliminate the constant, and we've got 1 is equal to 2/3 and then 2 to the 3 halves plus this constant. So the constant turns out to be rather an awkward expression, is 1 minus 2/3 2 to the 3 halves. You could leave it as that. That's a perfectly valid solution, or you could just pop in on your calculator that this comes out to be minus 0.8856. Slightly unusual for an exam question here. This was taken off the 2009 exam, that it doesn't come out with the usual very convenient constants coming out as integers, but that's life, that's the way it's turned out. And our final solution, the particular solution, including the boundary condition, is y is 2/3 1 plus x to the 3 halves over x squared minus 0.8856 over x squared.